Good morning. How's everybody doing? Oops, I forgot to turn on my video. Give me 1 second. And we're here. We made it. Well, as everybody knows, we've been having internet issues. So thank you so much for those who are watching. I wasn't even sure if we are going to stream this morning. And so, of course, apologies from me. I've been slow on grading. Obviously, we've all had intermittent internet issues for the past 2 days. And so I'm a little behind. And if your quizzes have messed up, let me know. I've fixed a few of those already. And I expect there'll be more since last night it sounded like the internet went down. Well, I woke up to it down this morning and I did call Spectrum. So I heard it's been down since midnight at least. And I know it's a mess. So obviously, I'm going to be very forgiving with the due dates. I'm just glad I'm here streaming, so I'm able to get out some content to you guys. Welcome to those of you that are live. I'm glad you were able to make it here as well. It's been a crazy quarter already somehow. All right, so I do have a meeting, so I'll have to end stream a little bit early today, but I think we'll still have plenty of time to go into our electronic structure. And so let's look at hydrogen. We're going to start back with hydrogen. And today we're really starting to answer, why do things react the way they do? Why do things make certain compounds? And so definitely ask questions. And I'll start to get into kind of, I think it's chapter 3 with the electron configuration. I think that's when we officially cover it. But it's good if we start looking at all these things now, even though it may feel like a lot, because then we can go kind of slow, but then I think it'll feel good later. And so with this, I would also recommend having up your P table. So I'll post another link. And so now if you look up top on P table, I would click on this electrons. And so this is going to be useful. And we're going to take our electronic tour. And so let's start with hydrogen. And so we said we wanted to start with hydrogen. And so if we remember, right, it has an atomic number of 1, and that's its proton. And so hydrogen then just has 1 electron. And so now we're starting to get into a little bit of quantum. I won't go into it too much, but just a little bit more understanding. And again, this may be covered later, but it's good to start seeing it now. And so we have our sphere here. And so this is representing our 1s orbital. And you can see it here. So this is the electron configuration, so the 1s. And so these s orbitals are just 1s orbital. And so that's always the case. And it looks like a sphere. And it can hold 2 electrons. And so sometimes we can write, so let's write 1s1 here. And so later we'll kind of see the pattern. And so I'm going to write the electron configuration already. And so the electron configuration is just kind of telling us where the electrons are and how many. And so now we're saying we have our 1s orbital. Again, it's just our lowest orbital of all our atoms. So that's what we fill in first. And it has 1 electron to be neutral with that 1 proton. And of course, right, this is neutral. Hydrogen, we write it like that. And so let's continue looking at this. And so now helium is over here. And so if we go back to P table, we'll see that helium, they put it in the s block. So what they're trying to show is helium does not contain any p orbitals. And what this periodic table, though, is trying to show is that helium is relatively stable and unreactive. So it's a noble gas. And so with this, I'll say So it has a 1s2 shell. And right, we could put helium over here because it's really 1s2. It's part of this s block. But I'll add to this satisfied by duet rule. And so all that means, and that only applies to hydrogen and helium, is that they only need 2 electrons in their s orbital, and then they are satisfied, so they have enough bonds, and they are kind of happy, as we call it. And that's just because their orbital is filled up, and that's the only orbital that they contain, is that 1s. So as long as it's satisfied, they're happy. And so if you've taken chemistry before, you may have heard of the octet rule, and that's kind of the standard rule. And we'll see where that comes from. So we'll go back to it. This is octet rule. But I want to wait till we show all the orbitals so we can get back to octet. All right, so let's continue our tour. So we're still taking our tour along. And so now we're back at this column. So we're back at the S block. And so you may want to do this on your periodic table, like an electronic one or another one. It all depends on your preference style. But this is all our S block. So their valence electron is going to be in the S block. So lithium, and so when you fill in the electrons, right, you still have to start at the beginning. So lithium, so it's atomic number 3. So meaning it's going to have 3 electrons for neutral lithium. And so we still have to start at the beginning. So 1s2. So we fill it up all the way, right? So 1 electron, 2 electrons in the S. Now we're back. So now this starts the 2s right here. And I would write 2s when you do the electron configurations. It matches. And so now we can write our electron configurations. So I just did helium right now. So that was 1s2. Now lithium, the next element. So 1s2, 2s1. And so let's visualize that. What is that telling us? Oops. There's my P table. And so if we look, so kind of look at this lower right-hand corner there, and it's showing us, so we have our first onion shell, so our 1s orbital. Then there's a space all the way around. So if you can like envision like a space, and that's called a node. And then after that, there's like the next sphere onion ring. And so that would be the 2s orbital. And so that's shown in blue. You can see the 1s is like that tiny little sphere in the center. And so again, we're just going in order. And if you ever have done any other tricks in chemistry, I know there's like those diagonal tricks to help you fill it up. This is the same order. And I think this is better because, you know, you just go across the periodic table instead of trying to learn any tricks and stuff. It all fills up normally. And then this is also giving us a deeper understanding, like compared to the Bohr model, which you may have been exposed to before, but we'll see how it matches. And so now let's look at kind of our more elementary Bohr model that you may have seen before. And it usually goes something, 2, then 8, 18, 32. So now we're really answering where all these levels come from. So this is our n equals 1 shell. So that only has our s orbitals with our 2 electrons. So that's that right in there. So now we're on n equals 2. And so going back to our periodic table tour. So beryllium is then 2s2 for its electron configuration. And let's go ahead and write it again. We're being really explicit right now. And so some other ways you can write electron configurations. So right now it's not too bad, but eventually, once we're looking at elements, down here of lead or curium, it's going to get cumbersome, right, to start writing 1s1, 2s2, blah, blah, blah. And so chemists then will say, well, let's write it shorthand. And so that means go to the previous noble gas, so whatever is over here, so this previous number. So it's easier to go numerically, like when you get over to this area like erbium, is 68. You want to go back to, that'd be 54 on the noble gases. And so right now we're just here. So the only noble gas we can go back to is helium, and doesn't save us too much pen ink, but we could still do that. So beryllium then would be helium. So starting with helium's electron configuration, and then 2s2. And then again, if you're in the chat, ask questions. This part either makes sense to people or doesn't. All right, so now we continue forward and we end up on this side of the periodic table. And let's highlight this. And this is our P block here. And so our P block, what is this kind of telling us? We're not want to write it. Ah, here we go. Actually, there's some notes down here. So we had our s orbital, and so this is our p orbital. That's helpful. And so there are 3 p orbitals, and each orbital holds our 2 electrons. So that would be 6 total in the p. And so this is what they look like. We can go back to P tables. So if we go over to borons, now it's showing us, and it just picks one of the P orbitals. So if we click on it, and you can kind of see that X, so it's going X with a line there. So that tells you that that's PXY, so a little lobe. And it just picked one of them arbitrarily since we don't really know. But okay, we're assigning it to PX. So we could have assigned it PZ as well. And our electron is in there. And so we can just write it here. And this is still 2. So this is 2p1. Then we go over. So 2p2, right? 2p3, etc. So 2p4, 2p5. Now notice neon. 2p6. So now it has a filled, right? 6 orbitals. And now it would be satisfied. So if we go back to this periodic table, we're doing our ends. So 2p1, 2p6, and that goes back to satisfied by the octet rule since it has, right, 2 electrons from our s orbital, 6 from our p, so that second energy level is satisfied, which matches, again, with kind of that elementary school Bohr model. And so now let's take a second. So let's do oxygen. Let's do oxygen's electron configuration. I'll take a second to do that. And you can write it out in the chat. And so we can go over it. And so let's start from the beginning. So we'll start from helium, the previous noble gas, or 1s2, and then it goes helium, then 2s2, so fill it up, and then 2p1, 2, 3, 4. And so now we can say a few other things. So this would be our core electron. So anything that's not the valence. And well, what are the valence electrons? So they're the outermost ones. In this case, our outermost shell. And so these valence electrons are important because, again, they kind of dictate the reactivity. So oxygen, right, has 6 valence electrons. And if we go back to our periodic table, so things start to fall into patterns. So this is, again, what drives the behavior. So what kind of compounds this family all makes. And so look at the 6 up here. So it's written both in Roman numeral or in just plain 6 here. And so this corresponds with the valence electrons, right? So oxygen has 6 and all of these. So sulfur has 6, selenium has 6. So, right, we're noticing patterns. Even though we're adding kind of more onion shells, it keeps repeating the valence electrons. So nitrogen has 5, carbon has 4, boron has 3, fluorine 7, neon 8. So all ton of information on the periodic table. So always want to have yours handy. So let's continue kind of this repeating pattern, and we'll add something else in there as well that's coming next term, or not next term, next week. Internet's got me all crazy. And so we're back at sodium. And so what can we say about the alkali metals? What's kind of been their pattern so far? Or what can you say? How many valence electrons do you have? And maybe this explains the reactivity. Yeah, exactly. So the alkali metals all have one valence electron. And so they're in this pattern of NS1. So we're just going down. So we started, right, 1S1, 2S1. So now sodium starts our third level. So our 3S. So this is 3S1. And so with them only having one valence electron, that's why they're so reactive. So that's why they're so water reactive, because that one valence electron is ready to fly off then because it wants to be satisfied by the octet rule. And so right now it's not. And so the easiest way to get back to the octet rule is to just get rid of this one electron in the outermost valence electron. And so notice too, of course, as our shells get bigger and bigger, right, our electron gets further and further out. And that's also why it's more reactive. So, of course, as that electron is further out from the nucleus has a less tight hold on it. And so it just flies off essentially. So we saw that with potassium, how it started getting really reactive. And so that starts the 4S down here, rubidium 5S, 6S, 7S, and all in that same pattern. And so now I'll kind of introduce Lewis dot structures, which is coming, but it's kind of good to teach them together. And so again, in middle school or high school, you may have been taught different but erroneous things about our Lewis dot structures. And so our Lewis dot structures And actually, let's make a new table so it's clear. And so again, our Lewis dot structures will be pretty repetitive, but the way that I like to think about them is so you have your atom A, whatever. And so you have four sides. And so each one of these sides you can treat as an orbital. So when we draw these Lewis dot structures, we mainly care about our s orbital or our valence s orbital, and then our three p orbitals. And I'll just call these, py, px, pz. It doesn't matter. That's just a formality. We don't actually know what p orbital it's necessarily occupying, unless we start getting into more things, bonding, blah, blah, blah. But we're not there right now. And we can't know that right now. And so now let's go back to our alkali metals here. And again, we all agreed they had one valence electron. So that means they have this NS1, like we said. And so if we're filling in their Lewis dot structure, and again, it doesn't matter what side you assign as what orbital, but we can write this again. So the same information now in our Lewis dot form. And so for our alkali metals, we would just put one dot to correspond to our one electron in our s orbital. And that would be the same for all of them. So lithium, sodium, potassium, right? They're all the same. Oops, I got crazy with that cesium. So does that make sense? All right, we're back to our electron configuration. And so let's look at magnesium together. So now we're 3s1, 3s2 for magnesium. And that makes sense. So it's still in the S block. And then the alkali earth metals. Again, we're noticing a pattern. So how many valence electrons do they have? And I'll go ahead and we can write our electron configuration for magnesium. And I'll write it both ways. So we can start the longhand. So 1s2, 2s2, 2p6, and then 3s2. And then again, all these are our core electrons, leaving our 3s as our two valence electrons. Or we could write it in shorthand. So we go back to the previous noble gas, that is neon, 3s2. I would accept both of those answers. And so matching this pattern, so NS2, and this is where you might see some different things. And this is my warning and kind of what matches. So sometimes you see magnesium in the textbook, or maybe you've learned in the past like this, because they usually simplify the candy rule a little. There's like distribute, one electron to each side until they all have one electron or one candy, and then you repeat. But that doesn't match with how the orbitals truly fill. So we were just learning that we have to fill our s orbital first. So that has to happen. But then the p orbitals, that's where that candy rule applies to. And so we can go back. Let me write this over here. So our p orbitals, and we probably should have set this over here, but when you write them like this, they are degenerate, which means they're the same energy level. And if we're writing then, or we're filling in our orbitals, so let's do this together. So let's look at oxygen. And so let's mark this out. So that's not really right. So better is magnesium with 2, because this is showing it's filling up the s orbital. So we want it to reflect this. But now let's just go back to oxygen. So this is, right, our electron configuration. And so we'll write it out this way. We can represent our energy levels with little lines. So each one of these lines is an orbital. As we go on, I think it's the next chapter or this chapter. I have to look at the book again. But you'll see a little box notation as well. And so I can write that. So you might see like this 2s, like 2p thing might be labeled. And then they fill in the electrons in the box. I like these lines personally. But let's translate the electron configuration to this diagram. And so first we need to fill in our 2 electrons in our s orbital. And I'll do that the same with this diagram here. And then we have 4 electrons in our p. And so this is where that candy rule applies. So 1, 2, 3, since they're all degenerate. So it wants to just put an electron in each one. And that's because you have to pay a small price to pair. So there's the repulsion energy. So there's kind of this energy price that you pay to pair. That's why it's more favorable to put them in the degenerate or same level energy orbitals first. And so then we end up with something like this. And let me fill it in on bottom. So depending again on the representation. And so now this matches right with our Lewis dot structure as well. So I kind of have jumped ahead. But it was good to show. And so oxygen, I want to fill in my s orbital first, so it doesn't matter what side I pick. And then 1, 2, 3, 4. And so that would be right our Lewis dot structure for any group 6 then. So that would be NS2, E4. All right, let's continue on with our electron configuration because things do get a little weird. Now we're back at our P block. So right, this was 3P, or this was 2P. So now we're at 3P at aluminum. So argon finishes out with 3P6. Oh, and just as a reminder, this is on your P table. So let's look at argon. You can both see it represented by the little pictures. So you can see right the 1s, 2s, 2p, 3s, 3p filled in. So that is there for you. Or it's also written out in the expanded form and in the electron configuration form. So that's a good check. And so now let's continue. Again, just filling normally. So we're at potassium, 4s1, Now calcium 4s2. Now we're here. So what is this? So this is where things get a little funny. So we were at the third energy level, but I didn't tell y'all that at the third energy level, we have a different type of orbital that can now happen. And so now at our third energy level, we have Ds. Now our D orbitals. So 3D is our first one. And so these D orbitals, there are 5 of them. And I don't think I ever make you draw them. You might want to be able to draw these. Not necessarily in this course, but eventually, maybe if you were to continue in chemistry. For now, just appreciate them. Appreciate that there are 5 of them. And then each one of them holds 2. And so that would give us 10 electrons total then. And so with all of these tricks, so notice, right, we said there were 2 in the S. Well, the S block is only 2 across. We said there were 6 electrons in the P. 1, 2, 3, 4, 5, 6. And so now our D block here, and we could highlight this. Highlight all of our D block. And our D block is 10 across. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is scandium is 3D. So write that in there, 3D. I'm trying to show that. It gets a little crowded on here. And so now we continue on. And so let's look at some oddities. Now's a good time to. So let's look at our P table one to help us. And so this is filling like we expect. So we see our 3D one here. Then titanium. So that would be 3D2. Vanadium 3D3. And now look at chromium. So we were at, so let's go ahead and do that together. So let's write vanadium's electron configuration. So take a minute to do vanadium. I'll put it back on screen then. See if you can fill it in. And so let's look at it. I'll pull up the P table, but let's go through it. So we were at argon. And we can look back at this one as well if it helps us. And then argon, go down to 4s2, then vanadium 3d1, 2, 3. All right, so we're there. Now try chromium. So chromium is right next to it. So what do we expect for chromium? So put chromium kind of expected here. So it's right next to vanadium. And so if we look at it, And this is what I just expect on the exam, right? So we don't have any other information, so we're just filling normally. And so I would expect it to be 3D4. So argon 4s2 3D4. And let me write that out. Well, actually, we'll write it later. I'll write it out. So 3D, so we have our 5D orbitals. Can't speak this morning. 5D orbitals are 4s. So I'm just writing this in pictorial representation. So that's our expected. But if we check ourselves with P table, we find, oh, come on, P table, that, oh, what happened? So if you notice, right, one is gone from the 4s, and instead we have 5 filling up our d orbital. And so I don't expect you to know this or be able to pick out when it's going to happen. But what could happen on an exam is I might give this scenario is the expected is this, and this is the actual, and I'll go through it. And so on an exam, you might have to explain why this happens. So 4s1, 3d5. And so what happens is each subsequent energy level is closer and closer in energy. And so what that is saying is the biggest energy level gap is between the 1s and the 2s. And then but each one gets smaller and smaller and smaller. And so then by the time we're at this one, what's actually happening is the 4s and the 3d are pretty close in energy. And remember, we said we had to pay a price to pair electrons. And so it is actually more energetically favorable then to not fill our s orbital. And then instead, so we have 1, 2, 3, 4, 5, 6 of these electrons. And now we can put each, the 1, 2, 3, 4, 5, 6. Now each electron is in its own orbital. So it's not paired. So we don't have to pay that energy price. So this is actually more favorable energetically. And so that happens a few times throughout. Let's kind of look at that. Let me pull up my. And so if we go back to, so now manganese is back to what we expect. So 4s2, 3d5 there. And then iron fills up like normal. So now we're at 3d6. 1, 2, 3, 4, 5, 6. Cobalt is normal. Nickel's about what you expect. Copper, notice you have that weird thing again. So it wants to fill up that 3d10 instead, leaving 1 in the 4s. And then zinc is filled, so that's, again, what we expect. So that looks good. And let's go back over here. And now we're back at 4p. And don't forget that, right? 3D back to 4p. So 4p, so krypton is 4p6. And then continue. So 5s1, 5s2. This is now 4d. Continuing on down. And then again, you might see the same oddities. So let's pull up our P table again. And yes, so molybdenum does the same thing chromium did. And does silver do the same thing? Yes. So again, those similar sort of oddities. Go back. So 4D. Just make sure you write that. Now we're back. 5P at indium. So going through. So xenon. 5P6. Now we're back. So this is, again, where things get weird. And so pay attention. So now we're at 6S1, 6S2. Now, what do we do here? And so I'm not quite a fan of this periodic table. And so first of all, you want to count your periodic table. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Well, why is that significant? Well, here we're adding, and let's just label this our F block. And so our F orbitals are down here, and there are 7 of them. And now I've never drawn these. I have drawn D orbitals. I give up at F, so just appreciate them. So again, there are 7 F orbitals. Each holds 2, just like before. So that gives us 14. But we counted 15. And your periodic table may differ. So sometimes you can find different ones. But I think the best consensus is that we put lanthanum over here. So lanthanum is 57. And so it's 5D1. And let's write that electron configuration. So we're on the same page. And this should match with P table, if I remember correctly. Yes. So P table agrees. But what's kind of weird, and I don't understand this, is it color-wise, it puts lutetium in the D block, but I wouldn't do that because the electron configuration says that lanthanum is. So watch out with all these different periodic tables and resources. They all have funkiness, as I call it. All right, so lanthanum is 57. So let's go back to xenon, which was 54 for our electron configuration. And let's go back to this periodic table. And so that is 6S2, 5D1. And again, that matches with P table. So now let's go over to cerium. And so cerium fills up how we would expect, again, how we're being taught. So now cerium, so the F block starts at our N equals 4 level. And so just like we would expect. So we're at 5D1, and then the next one is 4F1. And especially as we get into these weird ones, a good way to double check your work is all your little subscripts or superscripts should add up to the number of electrons you have. And so you can start with the number, your noble gas. So xenon has 54. And then plus 2 plus 1 plus 1. Probably didn't need my calculator, but oops. Now my calculator led me astray. All right. So 58 is what we should have gotten. Double check. Cerium is 58. And we're just looking at neutrals right now. So the number will match. All right. So now let's see. And let's write that down. So 4F1. So that starts our F block. So kind of weird. And then now let's look at this next element. And this is come on, why aren't you? That was really weird. All right, so now the next element, presodium. I'm not sure if I'm pronouncing that correctly. There we go. So 59. And this is where things, again, now get a little weird again. Because now all of a sudden, we've gone from 6s2 to 4f3. And so, again, a lot of that has to do with those orbitals are really close in energy. So they're going to do some funky things. And so it depends experimentally how it is. So you might have different answers for this one, is also what I'm saying. So our next element, and so we could put right expected. We could just fill in how we expect, right? We're going in order. So xenon, 6s2, 5d1, 4f. Sorry, 4f2, right? So that would be okay. Again, actual, and actually goes from the D to the Fs. So 6s2, 4f3. And, there could be geometry reasons. We don't have a lot of information. So that's our actual. So things get weird in the F block. So the important thing is just have the correct number of total electrons. And so this kind of follows normally. So now 4f4, 4f5, or at least as normally as these things get. And then for some reason, element 64, gadolinium. Gadolinium. You can tell I don't work with those elements. So usually like europium is used in research. I see some compounds, lanthanides, actinides, or thorium. They're trying to do or make nuclear energy power plants from thorium, uranium, of course. Erbium, I've seen. Yeah, I'm not too familiar with some of these. But for some reason, this one, well, actually, this makes sense. So now we can kind of tease out why. So now, notice we filled in all our 7 f orbitals, so 4f7. And then once we get, so this is 1, 2, 3, 4, 5, 6, 7, 8. So once we get here to 8, instead of pairing up in the f orbital, it knocks it back to the 5d1. And notice they are in red because they're all funky. So again, just be prepared for oddities. So, and we might have predicted that. So if we had filled it in just from here, so 6s2, 5d1, 4f7, so we would have gotten it maybe. This is the actual, or, if you did do something like this, the 6s2, 4f8, we would say, okay, not ideal, but on an exam, I would accept it because at least you have the correct number of total electrons. These do get weird. All right, so I think I'll have to end early today. And so something else that I wanted to throw out there, I mean, I could also do office hours, like online streaming at a different time if that works for people. I was kind of hearing, maybe Friday evenings people would be free. I don't know if that works for other people in the class or if people are even interested. So send me some feedback by email or in the chat if you're here of just what you're thinking. And I could stream it over YouTube so people could watch it later, which would be the advantage. If I did it over Zoom, which is also a possibility. The only thing is it's a little bit difficult to record, so I'd have to record it locally unless we don't want it shared, which that could be an option for people if people would rather have a more private question answer session. Then I could do Zoom, but then that wouldn't be recorded. So different things to think about. Kind of depends what people are looking for. I'm going to go ahead and end the stream here for today. So we'll probably continue on Monday then with finishing up doing more electron configuration practice, and then translating that to the Lewis dot structure some more and getting all that down. So we feel really comfortable, or just kind of the basics of chemistry, because then we're going to use these foundations and how many valence electrons they have to start building compounds and showing how they react. It gets more exciting from here. All right. Thank you so much for being here. Again, I know everyone is experiencing intermittent internet issues, so we will work through those together. Thanks again. Have a great rest of your week. Hopefully, the internet stays on for everybody so they can do their work. Otherwise, just do it when we can. Don't worry, guys. All right. Thanks again. Have a great day.